Hello again. This is Matt 2115 coming to you from the College of DuPage. The title of this lecture is Concerning R Combinations with Repetition Permitted. Please be an active learner as you watch this video. In this section we ask, how many ways are there to choose R elements without regard to order from a set of N elements if repetition is allowed? A good way to imagine this is to visualize N elements as categories of objects from which multiple selections may be made. For example, if the categories are labeled 1, 2, 3, and 4, and 3 elements are chosen, it's possible to choose 2 elements of type 3, 1 of type 1, and all 3 of type 2, or 1 each of types 1, 2, and 4, and so on. So we denote these choices by these bracketed symbols here. And note that because order doesn't matter, this symbol means the same thing as this symbol, means the same as this symbol, and so it only needs to be counted once. So here is some definitions and notations. An R combination with repetition allowed, or sometimes called a multiset of size R, chosen for a set X of N elements, is an unordered selection of elements taken from X with repetition allowed. So if X is equal to, the set X is equal to the set containing X1, X2, all the way up through Xn, we write an R combination with repetition allowed, or multiset of size R, as xi1, xi2, all the way through xir, where each xij is in X, and some of the xij may be equal to one another. Let's do an example. So here we're to write a complete list to find the number of R combinations with repetition allowed, or multisets of size 3, that can be selected from the set containing 1, 2, 3, and 4. Observe that because of the order in which the elements are chosen does not matter. The elements in each selection may be written in increasing order, and writing the elements in increasing order will ensure that no combinations are overlooked. We have a strategy for counting those. So what we'll do is we'll start with all combinations that start with 1, 1. And we conclude that this is the only way that we can end up with that. Then we'll look at all combinations that start with 1, 2, with 1, 3, or 1, 4. All additional combinations that start with 2, 2. All additional combinations that start with 2, 3, 2, 3, or 2, 4, 3, 3, 3, 4, and 4, 4. And you see that systematically ensures that we cover all of these, and that means there are 23 combinations with repetition allowed. How could the number of 20 been predicted other than making a complete list? And that would be very difficult if the numbers were larger. So let's consider the numbers 1, 2, 3, and 4 as categories, and imagine choosing a total of 3 numbers from the categories with multiple selections from any category allowed. The results of several such selections are represented in this table, and you can envision more. So you see here is category 1, category 2, category 3, and category 4. And to separate 4 categories, you need 3 vertical slices. So this would represent we're taking 1 from category 1 and 2 from category 4. This would be 1 from category 1, 1 from category 3, and 1 from category 4. This would be taking all 3 from category 1. As you can see then, each selection of these 3 numbers from the 4 categories can be represented by this string of vertical bars and crosses. 3 vertical bars are used to separate the 4 categories, and 3 crosses are used to indicate how many items from each category are chosen. Each distinct string, we've studied strings before, of 3 vertical bars and 3 crosses represents a distinct selection. For example, this says you take 2 from category 1, nothing from category 2, 1 from category 3, and nothing from category 4. Thus, the number of distinct selections of 3 elements that can be formed from the set 1, 2, 3, 4 with repetition equals the number of distinct strings of 6 symbols consisting of 3 vertical slices and 3 X's or crosses. And this equals the number of ways to choose 3 positions out of 6, because once 3 positions have been chosen for the X's and the vertical bars are placed in the remaining positions. So the answer is 6 choose 3 or 20. This analysis can be extended to a general case. If we have n categories and we're placing our x's, we're placing our x's into these categories, and so the string of n minus 1 vertical bars, since we had n categories, they're n minus 1 vertical bars, and our crosses is the number of ways to choose our positions into which to place the r crosses out of a total of r plus n minus 1 positions. So that means, by the theorem, this is going to be r plus n minus 1, choose r. And now we've proven this theorem. I'll quote it again. The number of r commutations with repetition allowed, or multisets of size r, that can be selected from a set of n elements is r plus n minus 1, choose r. This is the number of ways r objects can be selected from n categories of object with repetition allowed. Let's do a word problem with this. A person giving a party wants to set out 15 assorted cans of soft drinks for his guest. He shops at a store that sells 5 different kinds of drinks, soft drinks. How many different selections of cans of 15 soft drinks can he make? So we want to think of the 5 different types of soft drinks as the n categories, and the 15 cans of soft drinks to be chosen as the r objects. So n equal 5 and r equal 15. Each selection of cans of soft drink represented by a string of 4 vertical bars, which separates 15 crosses, which represent the soft drinks. And so, for example, this represents a selection of 3 of this first kind, 7 of type 2, none of type 3, 3 of type 4, and 2 of type 5. So the total number of selections of cans of soft drinks of the 5 types is the number of strings of 19 symbols. 5 minus 1, 4 of them are vertical bars, and 15 of them are crosses. So the number of ways is going to be 15 plus 5 minus 1. That's the theorem. Choose 15. You do the calculation, you get 3876. Part B. If root beer is one of the types of soft drinks, how many different selections include at least 6 cans of root beer? Well, if at least 6 cans of root beer are to be included in the selection, you can imagine choosing 6 such cans first, and then an additional 9 cans. The choice of 9 additional cans can be represented by a string of 9 crosses and 4 vertical bars. For example, if 3 cans of root beer, in addition to the 6 initially chosen, none of type 2, 2 of type 3, 4 of type 4, and none of type 5. That would be an example. Thus, the total number of selections of 15 cans of soft drinks of the 5 types, including at least 6 cans of root beer, is a string of 13 symbols, 4, that's minus 5 minus 1, or it's 5 minus 1 of them vertical bars, and 9 of them crosses. And so that, by the theorem, is going to be 9 plus 4, choose 9. or 13 choose 9 is 715. Part C. If the store has only 5 cans of root beer, but at least 15 cans of each other type of soft drink, how many different selections are there? If the store has only 5 cans of root beer, then the number of different selections of 15 cans of soft drink of the 5 types is the same as the number of different selections that contain 5 or fewer cans of root beer. Let T be the set of all possible selections, assuming there are at least 15 cans of each type. So R less than or equal to 5 is the set of selections from T that contain 5 or fewer cans of root beer. And let R greater than or equal to 6 be the selections from T that contain 6 or more cans of root beer. Then T, which is the union of R sub less than or equal to 5 union R greater than or equal to 6, with their intersection being null. So by part A, we know there were this many elements in T. And by part B, there were this many elements in R sub greater than or equal to 6. So by the difference rule, again the sets had to be disjoint, the number less than or equal to 5 is this minus this is equal to 3161. So there are only 5 or fewer cans of root beer. The number of different selections of soft drinks is 3161. Another example, let's talk about counting the number of possible triples, and this is of the form I, J, K, with 1 less than or equal to I, less than or equal to J, less than or equal to K, less than or equal to N. So we're going to let N be a positive integers. How many triples of integers 1 through N can be formed in which the elements of the triple are written in increasing order, but not necessarily distinct? In other words, how many triples of integers I, J, K are there with I less than or equal to I greater than or equal to 1, less than or equal to J, less than or equal to K, less than or equal to N? Well, any triple of integers I, J, and K with 1 less than or equal to I, less than or equal to J, less than or equal to K, less than or equal to N can be represented as a string of n-1 vertical bars and 3 crosses, with the positions of the crosses indicating which 3 integers from 1 to n are included in the table. The table below, in the triple rather. The table below illustrates this for n equaling 5. So you see we're trying to pick here, the selection is going to be 3, 3, and 5. 3, 3, and 5. 1, 2, 4 is 1, 2, and 4. And there should have been an X in this one. Anyway, the number of ways that we can do this then is that it's by the theorem. It's the same as the number of strings of n-1 vertical bars and 3 x's. So that is going to be 3 plus n-1, choose 3. And we do the calculation and we get n times n plus 1 times n plus 2 over 6. This is a formula you want to remember. Now, note that we were drawing pictures rather than using the theorem. You could have done either one. It depends on which you like better. Now, let's apply that to computer science. We can count how many times the innermost loop will be executed here. You see, we start with k equal 1 to n, but then we go from j equal 1 to k, and then we go from I equal 1 to j. So we do this loop every time, and what we want to do is we want to count and understand how many times the innermost loop, which in this case is this one here, when the algorithm segment below is implemented and run, how many times will the innermost loop be traversed. Okay, so what we can do is construct a trace table for the values of k, j, and I, for which the statement in the body of the innermost loop are executed. So you see we start with k going 1 to n, but then j goes all the way up to whatever the number is. So we start at 1, but then we go to 2, and so on. And so we can count those, and then we also know what happens with I for each one of those. Because I goes from 1 to j, is always the case that I is less than or equal to j. Similarly, because j goes from 1 to k, it always happens that j is less than or equal to k. To focus on the details of the table construction, consider what happens when k equals 3. In this case, j takes on 1, 2, and 3. And when j equals 1, I can only take the values of 1 because I is less than or equal to j. When j equals 2, takes each value 1 and 2. When j equals, again, because I is less than or equal to j, when j is equal to 3, I takes each value 1, 2, 3, and yet again because I is less than or equal to j. Observe that there is one iteration of the innermost loop for each column in the table. But that's the same thing as saying one column of the table for each triple of the integers I, j, k, where I is less than or equal to, I is greater than or equal to 1, less than or equal to j is less than or equal to k, less than or equal to m. Actually, that's n. So this is the same number that we had before. It's going to be n times n plus 1 times n plus 2 all over 6. Let's apply that to determine the number of integer solutions of an equation. And so this question would be posed as, how many solutions are there to the equation x1, x2, x3 plus x4 equal 10? If x1, x2, x3, and x4 are non-negative integers. That means that this is 0, 1, 2, 3, and so on. Well, we can think of the number 10 as divided into 10 individual units. And the variables, x1, x2, x3, and x4, are categories. So this is x1, these are x2, this is x3, this is x4. Now each solution can then be represented by a string of 3 vertical bars to separate the 4 categories and 10 crosses to represent the individual values. For example, in the following table, this has 2 crosses under x, 5 crosses under x2. This is x1, that is x2. This is nothing under x3. And this is 3 under x4. So that tells me that the answer for this, represented by this, is 2, 5, 0, and 3. Here's a different representation. Now, therefore, there are as many solutions to the equation as there are strings of 10 crosses and 3 vertical bars. That's 13 choose 10, or 286. Let's look at some additional constraints that we can have. How many solutions are there to the equation x1 plus x2 plus x3 plus x4 equal 10 if each x sub I is greater than or equal to 1? In this case, imagine putting 1 cross in each of the 4 categories. Then we're going to distribute the remaining 6 crosses among the categories. Such a distribution can be represented by this string of 3 vertical bars and 6 crosses. And so this ends up that we have 3 crosses in category 1, 0, and so forth. So this is, there are 3 more crosses in category x1 in addition to 1 cross already there, so x1 is 4. And this is no crosses here, but 1 was already there, and so on and so forth. It follows that the number of solutions to the equation that satisfy the given condition is the same as the number of strings of 3 vertical bars and 6 crosses, namely 6 plus 3 divided by, not divided by, but it's going to be 9 combinations taken 6 at a time. It's going to be 84. An alternative solution to this problem is based on the observation that since each xi is greater than or equal to 1, we can introduce a new variable, subtract 1, and solve it the way we did before. Now, this might seem really complicated, so here's a structure that will help you deciding which formula to use. If repetition is not allowed and order matters, it is in permutations taken k at a time. If repetition is allowed, it is going to be n raised to the k power, and that's if order matters. If order doesn't matter, it is n choose k when repetition was not allowed. If repetition is allowed, we studied it here, it is n plus k minus 1, combinations taken, k at a time. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.